Hi, my name is Jamie de Jong, and I created this video curve sketching for functions involving exponentials for the course MAT135 at the University of Toronto. The goal from this video is to be able to sketch curves of functions involving exponentials. So we're going to go through an example, and then at the end I'll leave you with a couple of exercises for practice. So the function that we're going to be sketching is e to the power x divided by 1 minus x. Now you'll see I've already filled in the details. That's just to save a bit of time so that you aren't waiting for me to write everything down, because there's quite a few things to determine here. So the first thing that we can determine is the domain that we're interested in for this function. So the domain of e to the power of x is r, all real numbers, and the domain of 1 divided by 1 minus x, is all real numbers, x not equal to 1, because we can't divide by 0. So that means the domain of this function is the reals that are not 1, and in particular the intervals that we might be interested in are negative infinity to 1 and 1 to infinity. So that's the domain of the function. The next thing that we're interested in that we can calculate just using this function itself is intercepts. So first, to find any y-intercepts, we set x equals 0. So we take f of 0, which is e to the power of 0 divided by 1. E to the power of 0 is 1, so this gives 1, and that means our y-intercept is 0, 1. Now for x-intercepts, we have e to the power of x over 1 minus x, and we set this equal to 0. So the x-intercepts occur when the function is 0. This means we need e to the power of x to be 0, and from our properties that we know for the exponential function, that never occurs. So that means there is no x-intercept, just the one y-intercept that we found. The next thing that we would like to determine is, does this function have any asymptotes? So we'll start with horizontal asymptotes. We can find this, as we determined a few weeks ago, by taking the limit as x goes to infinity and the limit as x goes to negative infinity. So in this case, the limit as x goes to infinity of this function, well, e to the power of infinity is infinity. 1 minus something infinite is something tending towards negative infinity. So this is of type infinity over infinity, and that means, as we learned last week, this week actually, we can apply L'Hopital's rule. And so we differentiate the numerator. This gives us e to the power of x. We differentiate the denominator to get negative 1. So we're now taking the limit as x goes to infinity of negative e to the power x. And we know the exponential gets infinitely large as x tends to infinity, so this tends to negative infinity. So we aren't getting a horizontal asymptote as x goes to infinity, but it's still useful to know this behavior. We're expecting the function to tend towards negative infinity. Now we'd like to look at the other potential horizontal asymptote as x goes to negative infinity. So the numerator, e to the power of x, we know goes to 0 as x tends to negative infinity. The denominator is tending towards infinity. And if we're dividing 0 by infinity, this gives us 0. So that means we have a horizontal asymptote of 0. So that's our only horizontal asymptote. Now we'd like to see if there's any vertical asymptotes, and really the possible candidate is the one where we're dividing by 0, so this value x equals 1, where the function that isn't in the function's domain. So we'd like to know what happens when x equals 1. And so as we tend to 1 from the right, e to the power x is tending towards e, which is a positive value. And we're dividing by something that's tending towards 0, but we're taking 1 minus something that is approaching 1 from above, which means we're getting something negative. So we expect our result to be negative, and we're taking a constant and dividing it by something that is tending towards 0. So that is tending to infinity. Therefore, the function goes to negative infinity as x approaches 1 from the right. Then we consider what happens as x approaches 1 from the left. And this time we're taking 1 minus something that is approaching 1 from the left, so from values slightly smaller than 1. That means we expect the result to be positive, and again we're dividing something that's constant by something tending towards 0. So we get infinity. So that means we do have a vertical asymptote when x equals 1, and we've also found the behavior as you approach from each side of this vertical asymptote. So that's about all of the information that we can find out without differentiating the function. We'd now like to see if there are any critical points. So we differentiate this function using the quotient rule, and we've got the result here. E to the power x times 2 minus x divided by 1 minus x squared. And critical points can be found when we set this equal to 0. So this derivative is 0, which means the numerator has to be 0. So e to the power of x times 2 minus x is 0, and that means one of those two factors is 0. Now, e to the power of x, as we've determined, it can never equal 0. So that means the only possible critical point is when 2 minus x equals 0, or in other words, when x equals 2. So that's our critical point, and we also need to know the y value at that point, so we'll calculate that here. We get negative e squared, which is approximately negative 7.39 for when we're trying to actually graph it later. So now we have our vertical asymptote at 1 and our critical point at x equals 2. So the next thing we'd like to determine is the function increasing or decreasing in the intervals on either side of these. So we'll apply the first derivative test. Remember, we found that on the previous page. And the intervals we're interested in are negative infinity to 1, 1 to 2, so that's either side of our vertical asymptote, and then 2 to infinity, so 2 being, in this case, the critical point, where we know the slope is 0. So we can test the derivative at a point in each of these intervals. So when we test this at 0, we get 2. When we test this at 3 over 2, we get 2 e to the power 3 over 2. Doesn't really matter too much what the exact value is. This is greater than 0, which means the function is increasing. And we'll calculate it at 3 for this third interval, and this gives us negative 1/4 e cubed. Again, we don't really need to know the precise value, it's negative. So that means the function is decreasing. So we've determined that the function is increasing on the first two intervals, negative infinity to 1, 1 to 2, and decreasing on the third interval, which was 2 to infinity. So that gives us a lot of the idea of the behavior that we need. But we also need to know something about the concavity and what kind of critical point this is. Certainly it looks like a maximum. We're increasing before it and decreasing after it. But we will need to check the concavity of this first interval because we don't know what's happening there. So let's calculate the second derivative, which I've given you here. You can calculate that using the product rule and the quotient rule. So, first question, are there any points of inflection? Are there any points aside from our vertical asymptote where the concavity might change? So that would occur if the second derivative is equal to 0. And we have the product of two factors here. So we have e to the power of x multiplied by this polynomial. Now, e to the power of x is never equal to 0. So that means in order for this product to equal 0, the second factor must be 0. And if we expand it and complete the square, we find that that means that x minus 2 squared has to equal negative 1 at a point of inflection. Now, x minus 2 squared is a positive number unless we're dealing with imaginary numbers, which we aren't. So it can never equal negative 1. In other words, there are no real solutions to this equation. And that means there's no point of inflection in this graph. So the only point at which the concavity of this curve could change is our vertical asymptote, which was at x equals 1. So that means we're interested in the intervals negative infinity to 1 and 1 to infinity. So we want to calculate the value of the second derivative at one point in each of these intervals. If you calculate the second derivative at 0, which is the easiest point in negative infinity to 1, you get 4. That's positive, that means it's concave up. If we calculate it at 2, the probably easiest point in 1 to infinity, and also our critical point in particular, we get negative e squared, and we know that's negative, which means it's concave down, and that means our suspicion was correct. This point is a local maximum. So that covers basically all of the information that we need. So I've got a summary here in bullet point form of the information that we found. So when we draw this, we have our vertical asymptote at x equals 1 and our horizontal asymptote at y equals 0. We know for values less than 1, the function is concave up. We know as we tend towards negative infinity, we tend towards this horizontal asymptote of 0. And as we tend towards 1, we approach infinity. So we've got that drawn here. And for values greater than 1, we expect a local maximum at 2 negative e squared. And we know as we approach 1 from the right, we tend towards negative infinity. And as we head to infinity, we tend towards negative infinity once again. So we've got our concave down function here drawn with the local maximum at 2 negative e squared. So that's what we were able to draw based on the information that we found in this video. And let's have a quick look at what Desmos shows it to look like. And we'll see that, yes, this does look much like the drawing on the previous page. So that's a good sign. So we've taken the function e to the power x over 1 minus x, and we've used the function itself and the first derivative and the second derivative to find out lots of information about its points of intersection, asymptotes, whether it's increasing or decreasing on certain intervals, whether there are any points of inflection, whether the function is concave up or concave down on the relevant intervals, and therefore we were able to draw a sketch of the graph. Now I'd like to leave you with a couple of exercises for some practice at this. So I've got 2 functions here that I'd like you to try and sketch using a similar process by figuring out all of the information that you can about the function and then trying to draw an idea of what it looks like. You can, of course, use Desmos to check that your answer is comparable to the function itself. If you have any questions, feel free to come to my office hours or ask on Piazza. Thank you.